Hey y'all, it's Professor Marinos again. In the first few videos that you watched, we learned about some properties of water and the solutes that you can find in water, as well as the potential sources for those solutes, be them anthropogenic, biogenic, geogenic, or atmospheric. And we're going to dive into that topic a little bit more. We're going to consider these sources not only as ways that solutes get into water, but also as sinks, or ways that solutes can come out of water. So how can these things that interact with water engage in a bidirectional transfer of materials with aquatic systems that we're considering chemically? And in this video, we're going to consider soil, rocks, and air to start off with before moving on to biota in the next video. So let's launch right into that. So by the end of this video, you'll be able to explain why particle size is a primary control on the reactivity of soils, describe how two different kinds of aquifers impact water chemistry, and name the two most important gases that water exchanges with the atmosphere. So, in the last lecture, we said that solutes can enter water from geogenic sources, from soils and rocks, minerals found in soils and rocks, biogenic sources coming from organisms, atmospheric sources from the air, and anthropogenic sources from people. And the first one that I like to focus on are geogenic sources of solutes in the soils. So, oftentimes when rainwater falls, the first thing that hits is soil. And when rainwater comes into a system, it bears atmospheric solutes that have been imparted by the rainfall into that water. And when it percolates through the soil and leaves the soil system, those solutes have been profoundly altered. A lot of those atmospheric solutes have left the water, and in their place, a lot of minerally derived geogenic solutes have taken the place in the water sample. So what controls the degree of this transformation of water as it moves through the soil, and the specific chemicals that are moved into and out of water as it percolates through the soil? So to begin this discussion, I first want to tell you about one of the most important ways that we divide up the minerals in the soil, and that's by their size. And why this is important will become apparent in a second. So we typically divide soils up into sizes of sand, silt, and clay. Sand is a particle that has a diameter between 0.06 millimeters and 2 millimeters. Silt is a particle that has a diameter of 0.004 millimeters to 0.06 millimeters, or 4 micrometers to 60 micrometers. And clay is anything that has a diameter less than 4 micrometers. And you can see here, over here is a relative explanation of the sizes of these particles if you were to blow them up. You can see if you said that sand was the size of my torso, for instance, this little silt particle over here would be about the size of, my fist, and a clay particle would be, smaller than the size of the freckle that's on my palm right here. So there is actually quite a huge range in sizes of soil particles that you see, and this very intimately controls the chemistry of the soil system. Now, why is this? Well, the chemistry of the soil system happens at interfaces between mineral surfaces and the water. And so the more those interfaces there are, the more active the chemistry can be in a system. And because the clay particles are so vastly smaller than these sand particles, when you consider their volume, this means that per mass of soil, you have much more surface area on a clay particle than you do on a sand particle. And silt particles are somewhere in between. But so the take-home message of this is that clay soils and clay particles have a lot of surface area where you have interactions between water and minerals, and this then makes them very, very active sites for soil chemistry to occur. Whereas sandy soils have very, very little surface area relative to their mass, and so as a result, these soils that are dominated by sands and sandy particles have less chemistry that are associated with them. So let's just take a look at some numbers of surface area. These will blow your mind. So for a pure sand soil, shown over here, per gram of soil, there are about 444 square centimeters of surface area on those particles. Contrast that with a silt here, you see that there are 111,000 centimeters squared per gram of silt particles. And clay there is 7 million centimeters squared of surface area per gram of soil. So you can see that in addition to having vastly different diameters, this is reflected also in vastly different surface areas, making clays orders and orders of magnitude more reactive than sand particles are in soils, simply because they have greater surface area. And so one of the most important ways that we classify soils is by their texture. And by texture, we just mean the distribution of sand and silt and clay particles in those soils. And here is a typical soil texture triangle that divides soils up. You have clays up here, you have sands over here, and you have silt soils over here. And the way that you can read this is this axis here is going from 0 to 100% sand. This axis here is going from 0 to 100% clay. And you can just follow these lines over. So say like I had a soil that was 50% sand and 50% clay. That would put me right here. And that would mean that I have a sandy clay soil. Or you can say you have a soil that is maybe 30% sand. Sorry, I'm trying to do this while being mirrored. And 60% clay. That will put you somewhere here in this clay territory. So these ways of describing soils are pretty fundamental to the way we think about soils for practical purposes such as agriculture, mechanical engineering involving soil substrates. And so particle size in soils is a pretty fundamental defining feature of soils, both for chemistry and for more mechanical applications. So in addition to determining the reactivity of soils, or the potential reactivity of soils, soil texture can also determine the amount of water holding capacity. So a sandy soil can hold a lot less water due to those adhesive and cohesive properties that we talked about last time. There's simply less surface area for water to adhere to, so that decreases its water holding capacity. Whereas a clay soil has a lot of surface area where water can adhere to, so clay soils tend to have much higher water holding capacity than sandy soils. It also determines the speed of water movement, and though that moves kind of inversely to the amount of water holding capacity. So a clay soil is very impermeable to water. It takes a long time for water to drain through a clay soil. Whereas with a sandy soil, I'm sure you can picture just dumping a glass of water on the sand of a beach. That water infiltrates extremely rapidly, and sand is very, very permeable to water. So water holding capacity and speed of water movement kind of move opposite to each other in soils. Also, in addition to controlling the rate of movement of water, it also can control the rate of movement of gases through the soil. So gas exchange to the atmosphere is controlled by the amount of barriers that air has to move through in order to get to water. And in clay soils with a lot of surface area, those paths to the water are very tortuous and long, and so this slows down gas diffusion. So gas diffusion from the atmosphere into water that's in the soil is much slower in clay soils than it is in sandy soils. And finally, it controls the minerals that are available for reaction. So oftentimes, sands are predominantly quartz, and quartz is a very non-reactive mineral, as you might know if you took Intro to Geochemistry. Whereas clays tend to be very, very highly reactive minerals, not just because of their surface area, but because of their chemical composition. And they engage in a lot of active exchange with water solution. So in addition to controlling the reactivity through surface area, it also controls the reactivity simply because some minerals are associated with the clay fraction that are more reactive, and other minerals are associated with the sand and silt fractions, which are less reactive. So another key player in determining the reactivity of soils, that is the kind of chemical reactions that will occur in soils and the extent to which they'll occur, is one of my favorites, again, soil organic matter. And this is just one example molecule, this is a humic acid, of a nearly infinite variety of soil organic molecules that exist. And you can see the chemistry is very, very complex, and it engages in a lot of complex chemistry with any solutes that come through the soil. And these reactions can include complexation reactions, adsorption reactions, oxidation reactions, a whole suite of reactions that we're going to consider later on in the class. So very complex chemistry and very abundant in the soils. Soil organic matter typically makes between 2 and 15% of the total composition of soils. Now, what is soil organic matter, though? Well, soil organic matter is dead living things, and ultimately, the source of any carbon that is in the environment is via plants. Via photosynthesis, plants fix carbon from the atmosphere, and they produce organic matter. And so roots and leaves are inputs of organic matter into soils that then drive the chemistry of these soils. But something that's very crucial that we really come to appreciate a lot over the last 15 or 20 years is that most soil organic matter is not actually directly from plants, but it has instead been digested and turned into microbial tissue, as shown here, and then these microbes are, they die in the environment, and then they become the soil organic matter that more directly interacts with the chemistry that you see happening in the soils. Or fauna, such as earthworms or little microfauna that exist in soil, like collembola, also play a very key role in transforming organic matter, such that most of the organic matter that you see in soils isn't directly plant matter, but it's the living remains of the things that had fed off plant matter in the past. So soil organic matter is plant matter as transformed by soil microbes and fauna. And again, nearly infinite variety and interest. So, we said that water enters an ecogeological system through rainfall, and it enters the soil. And in the soil, the solutes that exist in that water can be dramatically changed. Solids can be added and subtracted based on the minerals that exist in that soil. But now that water is in the soil, what's the next fate for that water? Well, that water can be taken up by plants. It can leave to the atmosphere via transpiration. Some of that water might flow into a stream and make its way on down to the sea. But a lot of that water will percolate into groundwater, or water that exists in rocks beneath the soil. And so I just want to touch a little bit about how the rocks that exist under the soil can also modify the chemistry of water. You didn't think you were going to escape a discussion of rocks in a geochemistry class, did you? So the first type of aquifer, or water-holding structure in rocks, that I want to discuss is unconsolidated sand and gravel aquifers. And these are just buried layers of sand and gravel that are under the soil that haven't been pressed into rocks like sandstone. So they aren't actually consolidated rocks. It's just loose sand and gravel that's many, many, many meters deep in cases, sometimes up to 1 kilometer deep. And these have varied sources. Some of these can be glacial outwash. Some of these can be erosion, like off mountains, for example. And so the sources of these rocks vary, and so their impact on the chemistry can vary a lot too. If the sand is predominantly quartz, as lots of sand is, quartz again is not a very reactive mineral, and so these aquifers won't have a very dramatic impact on chemistry. But if, say, a glacier ground up a bunch of different kinds of rocks and deposited it into one of these aquifers, that could have a substantially greater impact on chemistry. So I can't say exactly what it will do to chemistry because it's very context dependent, but this is a major type of aquifer that you see in the United States. So up here, these gray lines show the extent of glacially derived unconsolidated sand and gravel aquifers. You can basically trace the line of glaciers, the line of glacial extent across the United States just by looking at where these gray aquifers are. Another hugely important sand and gravel aquifer is the High Plains Aquifer, or the Ogallala Aquifer. This supplies a ton of the water for agriculture in Nebraska, Kansas, Oklahoma, Texas. And this was a sand and gravel aquifer that was formed via outwash by erosion of the Rocky Mountains. Same with this aquifer here on the other side of the Rocky Mountains in Nevada. And then over here in California, you see another hugely important aquifer, which is the Central Valley Aquifer, which supplies so much of the water that is essential for production of fruit and vegetables in California, which is really the breadbasket of the United States. So this is the first type of aquifer that I want to consider, sand and gravel aquifers. Hard to predict what kind of chemistry will result from them, but something that's really, really important is that because they're sand and gravel, again, we said that sand is hugely transmissive of water. Water moves really, really quickly through sand and gravel. So a key point of sand and gravel aquifers is even if they don't modify the chemistry a lot, if you modify the chemistry of groundwater, say you introduce a plume of pollutants into a sand and gravel aquifer, those pollutants can travel very fast, very quickly. And so that is a key way in which sand and gravel aquifers can change the chemistry of water in conjunction with humans. It can really spread pollution around. Next type of aquifer that I want to hit on is simply a sandstone aquifer. So this is just a sand deposit like we see in these unconsolidated aquifers that's been subjected to a little bit more pressure. It's been consolidated. A lot of the pore space has been removed. So these are less transmissive, but you still have a good bit of water that can come out of these. And again, you'll see these are important in a large swath of the Rocky Mountain area, as well as in Upper Michigan over, God, this green screen is going to be the end of me, over here. And these have a lot of the same properties as unconsolidated sand and gravel aquifers. It's just that they have, reduced transmissivity because they've been more compressed together. So the next type of aquifer that I want to talk about is a limestone aquifer. And these are relatively geographically restricted in the United States. You'll see some down here in Florida. There are a lot in northern Indiana, southern Michigan, Ohio, and also there's a little bit over here in upstate New York, which can be important for local groundwater chemistry in upstate New York. But even though they're geographically restricted, these are super important for the water chemistry of the areas where they do occur. Limestone, calcium carbonate, is very, very readily dissolved. And so this results in a ton of carbonate and calcium entering into water solution. And this is what we call hard water. So if you've ever dealt with hard water, you've seen with lime that develops on your shower head. You get this crust of lime, and that's just limestone that's been dissolved at depth, transported to the surface, and then crusts up on your shower head. So hugely important for the water chemistry of areas, and also very important for the water flow paths, because water can erode this calcium carbonate limestone so easily. What you see a lot of development of underground rivers and caves, such as like Mammoth Cave, the largest cave in the United States, is in a limestone system that has been eaten away by water. So limestone, geographically restricted, but super important to the water chemistry where it exists. The last kind of aquifer that I want to talk about are fractured rock aquifers. And so these are igneous and metamorphic rocks that don't have any natural porosity. They're solid crystals. But water can enter these where you have geologic fractures happening due to tectonic activity. And these aquifers are also somewhat geographically restricted. There are a lot in the Appalachians, and there are a lot in the Pacific Northwest, but that's about the extent of them. But they're very important for chemistry again. And the reason that they're very important for chemistry is because these rock fractures are the first times that these rocks are exposed to water and exchanged with the atmosphere since their formation. So a fracture forms, water comes in, and that initiates the process of weathering of this rock. So this is like the very, very first time this rock ever sees any sort of aqueous chemistry. And so what results is that the minerals that are very readily dissolvable in those rocks dissolve away very, very quickly at first. And so this is a site of very rapid geochemical transformation of these rocks, and subsequently the water that comes into these systems is also subject to a lot of transformation. So we'll get a little bit more into what exactly these solutes are that result from water entering into fractured bedrock systems. But just know that these sites of fractured bedrock aquifers are sites where you see a lot of mineral exchanges occurring in waters. So the last system that I wanted to discuss today that interacts with the aqueous systems that are the focus of this course is the atmosphere. And I specifically want to focus on two very important gases that will be central to your understanding of aqueous chemistry. We can leave the rest of the atmosphere to do its own thing for the purposes of this class. The first of these gases is oxygen. So oxygen is 21% of the atmosphere, and oxygen is always diffusing into and out of water. It's a very important player that drives a lot of geochemical and biogeochemical reactions. So you can see over here You see this red film that's been created on top of this puddle of water. I'm sure you've seen this yourself out in nature somewhere. And this is simply iron oxide that is formed in water. What's happened is that iron-rich waters have come out of the groundwater, they've come into contact with atmospheric oxygen, and that iron-rich water has been oxidized to form rust. This is just liquefied rust, iron oxide, held in suspension here in this puddle. So oxygen can drive a lot of the geochemistry that you see. Oxygen can also drive a lot of the biogeochemistry that you see. So here on the right, we have a fish kill. This is caused by lack of oxygen. So fish came into contact with anoxic waters, and they very tragically bit the dust. And so this can drive a lot of the biology that you see. Aerobic organisms like fish can't survive without oxygen, but there are tons of anaerobic organisms that do very interesting geochemistry, which we'll discuss in the next lecture, that are driven by the amount of oxygen availability, which is in turn controlled by gas exchange with the atmosphere. So the second gas that I want to hit on is carbon dioxide. Carbon dioxide, as of this morning, I think I looked it up, I think it was 414 parts per million in the atmosphere, and unfortunately by the time you watch this video it's probably going to be even higher. Obviously humans have been driving the concentration of the carbon dioxide in the atmosphere higher and higher since the Industrial Revolution, and really since the Agricultural Revolution. But carbon dioxide is super important for aqueous chemistry because it's the source of carbonic acid. So carbonic acid drives the weathering of lots of minerals. It drives mobilization of metals and such. It decreases the pH in soils, potentially. And most importantly, it's decreasing the pH of the ocean, which is vitally important for the health of the ocean. Here you see coral reefs that are under an amazing amount of stress due to ocean acidification. And the reason is that coral reefs are made out of calcium carbonate. The exoskeletons of corals are calcium carbonate. This carbonic acid enters into the ocean, and it literally starts dissolving the exoskeletons of corals. So carbon dioxide is another key gas, both for weathering reactions and for biogeochemical reactions in the marine environment. So that's the end of this lecture. In this lecture, we've touched on how minerals in the soil and in bedrock control water chemistry, as well as how exchanges with the atmosphere can control water chemistry. And in each of these examples, we've touched on the subject of life. And life is really inextricable from geochemistry. I like to say that all geochemistry is, in essence, biogeochemistry in some sense. And so in the next lesson, we're going to explore a little bit more how life specifically modifies the geochemistry of systems. So I'll see you then.